Okay, I guess I'll take attendance right there and then we'll get started. While I take attendance, do y'all have any general college questions? Any questions that you have to rephrase or re-asked because of the global pandemic and what it's doing to higher education? No, no questions. That's weird. Okay. Are there any questions in general before we start, or should we just launch right into it? Or like if anyone's talking, you should realize I muted all of you. So please use the button to talk, which is spacebar. No, okay then. So item number 2, we're gonna graph and solve for an intersection. So out there, those of y'all who graphed this already, how many intersections should we get?
2.
2, really? Let me go ahead and switch off to my graph in Desmos, unless like potentially I made a mistake.
I don't know, maybe I'm wrong.
I believe that this is 3 intersections. So I have x minus 2 quantity squared, y minus 2 quantity squared is equal to 4. And just so that we're all reminded about how to read this equation, this is a circle centered at 2, 2. That's how we interpret the parts that are added or subtracted to the x and the y's. And then it has a radius of 2 because it's actually set equal to the radius squared. So that's our red circle here. And then our parabola is y is equal to x squared divided by 2 minus 2x plus 2. And that intersects this circle at 3 points, 2, 0, 4, 2, and 0, 2. Are there any questions about the graph?
Mr. Robinson, I did the same thing, except I put parentheses around x over 2, but I got a different graph.
Putting parentheses around x over, oh, I know what you did. I believe it's because you put parentheses around the x over 2 and then squared it, which actually gives you x squared over 4.
Oh, okay.
Yeah, because if you square a set in parentheses, I'm sorry, if you square a fraction, it squares the numerator and the denominator, and this is just supposed to be x squared over 2. And so we have a bunch of different techniques that we could use in order to solve for these values by hand algebraically. However, what I would like to show y'all is probably what the most elegant procedure is to get to the answer. So if we wanted to substitute in here, right, and just brute force it, what we would have to do is we would have to take this value for y, pop it in there, and then do a bunch of math, which would include squaring a term that had 3 parts. And what happens if you square a term that has 3 parts? How many terms are you going to produce?
9, right?
Yeah, you would get something that has 9 terms, and it would have x to the 4th, x cubed, x squared, x, and a linear term. And then we would have to take that new to the 4th power equation, and we would have to factor it down in order to get our 3 answers. That would be extremely time consuming and painful. And so what we're going to do is we're going to use the same sort of approach that we used in our second example yesterday, where instead of substituting in a term which is linear, we're going to substitute in a term which is squared, which is going to allow us to avoid most of the hassle of substitution and simplification. So let's go ahead and start by taking a look at this parabola right here. And I'm going to start by multiplying both sides of this equation by 2. This is going to give me 2y is equal to x squared minus 4x plus 4. And this is a non-obvious step, but here's what I noticed. This could factor if it was doubled. You'll notice now that I've doubled both sides of this equation, this right here is a perfect square factorial. What does this factor into? I need 2 numbers which multiply to +4 that add up to -4.
-2, -2.
Yeah, notice this is x minus 2 quantity squared. So this is to say that 2y is equal to x minus 2 times x minus 2, which is to say 2y is equal to x minus 2 quantity squared. And so instead of solving for y and popping that in up here, what much nicer substitution can I now make?
2y for x minus 2 squared.
Yeah, I can take this 2y and plug it into this x minus 2 squared. So this next thing that I'm about to write is actually the equation of the circle. So it's x minus 2 quantity squared plus y minus 2 quantity squared is equal to 4. But since I have a redefinition of x minus 2 squared, now I can say that this is 2y plus y minus 2 quantity squared is equal to 4.
Oh,
So now what must my approach be for solving this equation? What kind of equation is this?
a parabola.
This itself
Parabola.
is a quadratic, which I can now solve. And so I'm going to expand out the y minus 2. So this is 2y plus y squared minus 4y plus 4 is equal to 4. And what was the point of doing that? Why did I need to expand this term?
So we can factor.
So that we can recombine and factor. The deal with
Recombine.
expanding this out is the fact that I know that in here there's going to be a constant term, and that constant term ended up being 4. And I need to expand it out to see how it mixes with this other constant term. The other thing that I knew that squaring this would produce is a term with y, and I have to expand it out to see how this term with y mixes up with this term with y. Now that I've expanded it out to see what pieces are actually in there, I can go ahead and condense this down and solve that quadratic. And so I'm going to subtract 4y from, I'm going to subtract 4 from both sides. 4 minus 4 is 0. And I'm going to combine the 2y with minus 4y. So this is actually just y squared minus 2y is equal to 0. Is that okay? Are there any questions right there?
No, pretty good.
Okay. And so this factor is nice and easy. What does this factor into, y'all? What can I pull out of both of these terms?
Y.
Y. So this is to say y times y minus 2 is equal to 0. And so y is equal to 0, and y is equal to 2. So those are my potential y values. Now I need to figure out which x terms they pair off of with, right? And so let's go ahead and look at our 2 original equations, because keep in mind, solving either of our 2 original equations should give us back x. So which one of these 2 would you rather solve for x?
Maybe the second one.
I'm going to disagree strongly with you unless you're saying we should take it right here. This is nice and solve for x, but I don't like using this parabola to solve for x just because this is a quadratic. And so there would be two positions that we need to solve for x for. Instead, I'm going to use this top equation right here. And so we're just going to use the equation of the circle to solve for our potential x values. Let's go ahead and start off by solving for what our x value is when y is equal to 0. So that is to say x minus 2 quantity squared plus, well, if the y value that we're testing for is 0, I can just pop 0 in. 0 plus 2 quantity squared is equal to 4. And now let's go ahead and simplify and solve. So this is x minus 2 squared.
Mr. Robinson, it's 0 minus 2.
Plus 4. Sure. Doesn't make a difference in the end, right? Because negative 2 and positive 2 both square to 4. So either way, it's going to be x minus 2 squared plus 4 is equal to 4. X minus 2 squared is equal to 0. What's the square root of 0?
0.
0, and that's why this one is not going to produce two values, because when you take the square root of 0, you only get one value back. And so x is equal to 2. Now keep in mind, the thing that gave us that x was 2 was plugging in what value for y?
Negative 2.
No, here we plugged in
Negative 2.
0.
0.
We plugged in
Oh.
0 for y. And so by
right,
plugging
right.
in 0 for y, that produces the x value 2. That tells us that this ordered pair is 2, 0. So this right here is one of our solutions. And now I can solve for the other x values, which will be associated with our other y value. Y is equal to 2. So we can go ahead and plug that in and check that out. So that's going to be x minus 2 squared plus 2 minus 2 squared is equal to 4. 2 minus 2 is 0. 0 squared is 0. So this all goes away. And so this is going to give me x minus 2 squared is equal to 4. From here, what do I do?
Square root of 4. Square root of 4.
So I'm going to take the square root of both sides. So this is to say x minus 2 is equal to, what is the square root of 4?
2.
No.
Oh, plus minus
2
2.
and negative 2.
Plus or minus 2, which is big. And this is how we're going to get those other 2 points. And so x is going to be equal to 2 plus or minus 2, which is to say x is going to be equal to, well, if it's 2 plus 2, that's going to be 4. If it's 2 minus 2, it's going to be 0. And this is how we get the other 2 ordered pairs in our set, 4, 2, and 0, 2, along with our third coordinate, 2, 0, which we solved for up above. And so the algebra bears out the fact that we get 3 intersections of these 2 functions. Not 2, not 4, but exactly 3, 0, 2, 4, 2, and 2, 0. Are there any questions on today's warm-up?
No.
A very spicy question. Okay.
Mr. Robinson,
Yep.
you know how you somehow changed x minus 2 squared to 2y? Like, I know how you did it, but looking at the equation or looking at the problem, how should we know to do that?
It takes a long time to build like good, I mean, don't get me wrong, the actual way of how you should do this if you got stuck is plug in y and square that whole nightmare term and do it by brute force. The reason why I had the intuition to do this was the fact that I saw this and noticed that this is a perfect square factorial. And I mean, also, the other place where you should have an idea that maybe there's an easier way to approach the question was when you graphed it. You did graph it when you started off, right? And you noticed that the solutions were integers.
Right.
If you plugged in the points and the intersections in the graph were all like rotten decimals, that would indicate that the only way to do it is by some brute force method. But in cases like this where the answers are integers, there has to be some sort of nice alignment between the 2 equations. And in this case, that nice alignment was the fact that the x term in the circle equation matches what the perfect square factorial is for the quadratic. I would recommend, should you be given a question like this, try hitting the quadratic with complete the square. And if that aligns with your equation of a circle, it's a much cleaner substitution than just substituting across y and then using brute force. It's a great question. Are there any other questions out there before we wrap up the notes for this section? No, okay. And so the last little element that is in the notes for this section are how to deal with nonlinear inequalities. So when it comes to graphing inequalities, y'all have done this before, so this is actually just a review. It's just that I find that usually you only graph linear inequalities. However, I can totally ask you to graph nonlinear inequalities, and it doesn't require any skill past graphing nonlinear equations. It's really just 2 rules to observe plus 1 extra step. So when it comes to graphing, and this is section 9.3, continued. I won't add another header, just continue this along in your notebook. When it comes to the graphing of nonlinear inequalities, we have one thing that we need to consider first. Is our inequality written with a greater than or less than, or a strictly greater than, or a strictly less than? That's an important thing because it's going to tell us what kind of line we are supposed to draw the graph with. If something is drawn with strictly greater than or strictly less than, we need to use a dotted line. And why is that? Why is it that when we see this strictly greater than or strictly less than, we have to use a dotted line? What is this supposed to represent with respect to what these symbols mean?
The line doesn't have any solution.
Very good. The reason why we have to use this is that the line itself, right, the function values are not solutions. They are simply drawing the boundary where the solutions exist. This is simply due to the fact that if you take a point along the function and plug it in, you would get that the number on the left and the number on the right were the same. For example, you would get the statement 4 is less than 4. And is this statement true or false?
False.
Is 4 less than 4? Yeah, this is false.
Oh, that's
And that's true of all the function values. If you were to take this point right here and plug it in, you would get that 5 was less than 5 or 7 was less than 7. And because that's what every single one of the points along the function gives us back, every single one of the points along that function is actually false. It is simply acting as the barrier between where our answers are and where our answers are not. And that means that if we have greater than or equal to, or less than or equal to, we are going to use a solid line. And that is simply due to the fact that the function values are solutions in this case. Because again, if you plug in one of these function values, you would get, for example, that 10 was less than or equal to 10, which is now a true statement because of the addition of this equality symbol down here. Is this okay?
yeah.
Yeah, okay. So now that we have, you know, a quick reminder of that rule, which by the way, this is a great rule for dealing with multiple choice tests, because if you are ever dealing with a multiple choice test that has graphs of inequalities, checking to see that the type of line in the graph matches the type of symbol used in the equation can often be used to instantly narrow down 4 options to 2 options, right? The next rule is how we actually graph these, and graphing these is pretty straightforward. All that we are going to do is we are going to graph the function using the appropriate line And then we are going to choose a test point which is not on the line itself. You cannot choose a test point which is on the function. That will not give you any additional information. We have to choose a test point which is not on the function, and then plug that into the inequality. If the test point is true, if it satisfies the inequality, then we are going to shade towards that region. And if false, we are going to shade away from that region. We will know then to shade the other way. And then finally, I know there's a lot of if-thens here, but this is the logical flow that you want to take to dealing with these types of questions. Number one, is it solid lines or dotted lines? That's hard and fast based on the symbol. Number two, graph it like normal and then figure out which way to shade by choosing a test point and then figuring out whether or not we're shading towards or away from that test point. The last thing to consider is the fact that normally you'll be given multiple functions here, not just one. And so this is to say that the solution to a system of inequalities, right, multiple, is what? Who remembers, if I have multiple inequalities and we're shading a whole bunch of different ways, how do we know what the answer is?
The area where the shaded regions overlap.
Correct. It is the place where, right, the solution to a system of inequalities is where the shading overlaps. It's the same as saying it is the region of points where you could take any one of the points in that shaded region and you could plug it into every single inequality in the system, and it will give you back a true statement for all of those inequalities. So all I got for y'all is one simple example, and then we'll be done for the day. I'll also take this homework assignment and extend it one day just so that we're not starting a new section on Friday. And because, you know, these notes took 2 days, so we'll have tomorrow on Friday for our workshop. Is that cool?
Yeah.
Yeah.
Great.
Okay. And so let's go ahead and do the following straightforward example. Let's say that I have y is greater than x squared minus 4. Yeah, and I have y is less than or equal to 3 over 2x plus 2. So I'm going to do this by hand, and then we'll verify this in Desmos. So number one, what is this top function?
Quadratic or parabola.
That is a parabola when I graph it. And notice I want this parabola to be very easy to graph. And so what are its roots and how do you know? You should be able to read them right off there by inspection.
X plus 2, x minus 2.
X plus 2 and x minus 2, that's because this guy right here factors in a very straightforward way. This is equal to x plus 2 times x minus 2. Or we can also get exactly where it sits when we plug in 0. So what is y when I plug in 0?
-4.
-4. So here is this parabola. It has the point 0, -4, so -1, 2, 3, 4. That is one of its points. And I know that its roots are plus and minus 2 because it factors in this way. +1, +2, right there. minus 1 minus 2 right there. And this is x, this is y, of course. And what kind of line am I going to draw this parabola with?
A dotted line.
I'm going to draw it with a dotted line because this is a strictly greater than. There is no potential for equality. And so I'm going to draw my parabola out with a dotted line. I'm going to draw my parabola out with a dotted line. And now we need to choose a point which is not on the function to act as our test point. And given the ability to choose any test point you want, as long as it's not on the function, what is the best test point?
0, 0.
The origin is by far the best test point just because it's so easy to do math with the number 0. And so if I take 0 and I pop it in here to the original equation, this is to say 0 is greater than 0 squared minus 4. 0 is greater than minus 4. Is this true or false?
Both
It's true.
true.
This is true, which means that we are going to shade in the region with 0, 0. So with respect to our parabola, 0, 0 is right here. And so instead of shading down below the parabola, I'm going to shade upwards in the area that contains 0, 0. So the inside of our parabola is going to be our shaded region. Is that okay for the parabola?
Mr. Robinson, quick question. What if we're dealing with a line? Is it possible to have a line and then try to solve for inequalities?
This is a line. This is an inequality. I'm going to answer your question next by addressing the second part of this problem.
Yeah, I didn't see that. All right.
Okay. And so I'm going to start off by graphing this. And how do we graph a line? Where do we begin?
At the y-intercept.
We're going to start at the y-intercept. So I'm going to go up 2, so plus 1, plus 2. 0, comma 2 is a point on our line. And just so that there's some like variance here, I'm going to be graphing this line in red. Does that show up? Is that okay for y'all?
Yeah, it's
Yeah.
clear.
Okay. And then from there, I'm just going to count out the slope like it's 7th grade. So we're going to do a rise over run. I'm going to go up 1, 2, 3. I'm going to go over 2. So this point right here is also on our line. And does this guy get a dotted line or a solid line?
A
Solid.
solid line.
Solid line, because equality is part of this relationship. So every single one of the points on this line is also, sorry, every single one of the points on this line is also part of our solution. So there's my line. And now, again, I'm going to choose a test point. Since 0, 0 is not on the line, that's a perfect test point. And so this is going to give us 0 is less than or equal to 3/2 times 0 plus 2, which is to say 0 is less than or equal to 2. Is that true or false?
True.
True. And so this is telling me that from this line, I'm going to shade in the direction of our test point, which is the origin. And so for the line, everything below the line is the solution region. So does this system of inequalities have a solution itself?
Yeah, it does.
Yeah, and you'll notice that there are actually 2 different types of solutions that you could get. If there's no overlap, there's no solution. And in this case, there is a solution. It is this region right here, which I'm about to color in. It is bound on the bottom by the parabola, and it is bound on top by the line. And you'll notice here, right, that there is a boundary on every single side of this. So we consider this solution right here to be a bound solution. You will find times that the solution to your set of inequalities, one side of it might go off to infinity. Like if I were to flip this inequality and instead we were to shade upwards, right, then the solution region would continue going up forever and ever and ever and ever and ever. In those cases, you would have what's called an unbound solution. That's just a little bit of knowledge for your own brains and for next year in calculus. Knowing the difference between a bound and an unbound system is not part of this pre-calculus stuff. Don't worry, I won't be asking about that. Now let me, do I have time? Okay, yeah, cool. We still have a few minutes and then we'll just take questions and hang out until the end of class. Let me show y'all how to do this in Desmos, because Desmos can do this. So over here in Desmos, I'm going to start off by delete my 2 equations from the warm-up. And so all I have to do is type these in, and you know, your keyboard has inequality buttons. So it's going to be x squared minus 4, which is nice. And as you pop it in, it will automatically shade that region. Is this okay? Do y'all see that?
And it's in dotted lines too. It's pretty good.
Yeah, and it knows also to do the dotted line. You know, I actually don't even know in Desmos how to do greater than or equal. Oh, okay, it's down here in the keyboard. You'd have to open up the keyboard just because there's not a standard key on your keyboard for greater than or equal to. And when we do it in coding languages, you actually do a greater than with, let me see if it works here. Nope, it doesn't. It does an absolute value. Anyway, in coding languages, there are shortcuts for greater than, equal to, and less than equal to. Anyways, equation number 2, y is less than or equal to 3/2 x plus 2. And you'll notice here that that one tells us to shade down. And so the overlap of these 2 regions is the solution region, this weird shaped piece right here. Now let me show you what I meant by the unbound part. So if I were to take this inequality and flip it, now the solution region, the overlap of the 2, is technically this part up here. And notice, does the solution region ever end?
Does not.
No, it doesn't. So long as I keep pulling back and generating more and more graph, there will be more and more and more and more components within our solution region. That is what's known as an unbound solution, a boundary that technically, I'm sorry, a solution region that technically has infinite area. Let me go ahead and flip it back. And there's our bound solution, where you could describe how much area is in our solution region, and that area would have a finite number, which I know that you guys don't have the equations to do this with now because it's not a simple object. Like, you know how if you want to find the area of a triangle, it's just 1/2 base times height. If you don't know, calculus does actually give us the ability to calculate precisely what the area of this region is. And that's something you'll learn all about next year. Is this okay? Are there any questions on the second half of the notes for 9.5, systems of inequalities?
No, I think we're good.
Okay, so just so y'all know, that's it for notes on this section. I'm going to move stuff around in the class schedule so that we have one more day for this, just because today we were late to start and therefore late to finish. So tomorrow will be our workshop on 9.3. When y'all come in for lecture, the do now will be a system of nonlinear inequalities that I'll ask you to graph by hand first, and then we'll go over it together and look at it in Desmos, and then for the rest of the time we can work on the homework assignment until y'all are done with it. Are there any questions on what we're doing in class tomorrow, or any other questions just in general? No college stuff, no virus stuff. No, everybody's playing Animal Crossing instead of paying attention. That's cool. It happens.
Mr. Robinson,
Yep.
how about that new virus, the hantavirus?
That's not a new virus. The hantavirus is old and it's constantly in circulation.
Oh,
That's like talking about the new flu virus. Like, nah, the flu virus has always been out there. It's always been in circulation. It's just, it's having a flare up right now.
yeah.
Any other questions out there? No? Okay. Anyway, like always, these videos will get backed up and go on YouTube. I only have like, don't get me wrong. Like, I'm not telling you you have to go on and subscribe. But I was looking the other day and I was like weirded out that I only had like 2 or 3 subscribers for Precalculus. If you're absent to this class, like if you miss one of these recordings, don't at me. That is literally why there is a YouTube channel. If you miss a class, just go on YouTube, look up the class that you missed and give it a watch. You might as well get used to that freedom or whatever, just because for the most part, that's how college is going to be. At UCLA, all of the classes were podcasted, so if you ever missed a class, you could just like pull it up and listen to it at your leisure if it wasn't a class where the written notes were important. And there were a bunch of classes where I would just set it to multiple speed because I thought the professor talked too slow. So, yo, man, if you're just trying to play catch up or whatever, check out the YouTube channel, set the speed to 1.2 or 1.3 or whatever's a more comfortable listening speed for you than my normal talking speed, and get caught up. But yo, for real, don't at me about being absent. Y'all have a nice day, and I'll see you tomorrow. We'll be graphing another system of nonlinear inequalities, and it'll be Friday.
All right. See you, Mr. Robinson.